Welcome to another deep dive, and this time we're going to ride the waves of knowledge. We're diving into this presentation called The Nature of Waves. It seems like a really good, Wave Fundamentals 101 kind of thing, but, think about it. You encounter waves every single day. I mean, from the ocean, crashing on the shore, to the music you listen to in your headphones. Have you ever really sat back and thought about, what a wave actually is?
That's a great point. And what's so fascinating about waves is that it's all about energy transfer,
Yeah.
but not necessarily matter transfer. So think about if you're standing by a perfectly still lake, nice and tranquil. You toss a pebble in, all of a sudden you see these rings expanding outward. Those ripples are a wave. They're carrying energy outward from that point of impact. But the water molecules themselves are mostly just bobbing up and down. It's like a secret handshake, passing energy along the surface.
That's such a great visual. Okay, so are all waves created equal, or are there different types of waves?
That's a great question. There are two main categories. We've got mechanical waves and electromagnetic waves. And understanding that difference is really key to kind of unlocking this whole diverse world of waves.
Okay, so let's unpack those categories a bit. What are mechanical waves?
So mechanical waves, they actually need a medium to travel, some sort of substance. They need something to like wiggle in. So, ocean waves need water, sound waves need air. Even seismic waves during an earthquake need the earth itself to travel through.
So it's like if there's no medium, a mechanical wave just stops. Like you couldn't have a conversation in the vacuum of space because there's no air for the sound waves to travel through.
Exactly, exactly. Without a medium, mechanical waves are silenced. Now, electromagnetic waves, those are the rebels. They don't need any material medium to travel. They can zip right through the vacuum of space at the speed of light.
Wow.
That's how sunlight gets to us from the sun. That's how radio signals travel across the globe. And even how X-rays can see inside the human body.
It's incredible how those waves can travel such vast distances without needing anything to push them along. Okay, so we've got these two fundamental wave types, mechanical and electromagnetic. Can we dissect a wave and see what it's made of?
Absolutely. Let's zoom in on the anatomy of a wave. And to keep things clear, we'll focus on the classic transverse wave, like the waves you see on the surface of the ocean.
Perfect. I always love those diagrams in science class with all the peaks and valleys.
Yeah. So those peaks are called crests, and the valleys are called troughs. Then we have amplitude, which is a measure of a wave's intensity or strength. Think about like a tsunami with its towering height carries immense destructive power. That's because its amplitude, the height of the wave, is massive. It's packing a lot of energy. And a larger amplitude generally means more energy being carried by that wave.
Oh, okay. That makes sense. So what about the distance between those crests? Is there a term for that?
Yeah. That distance is called a wavelength, and it's measured from one crest to the next identical point on the wave, which could also be from trough to trough. Then we have frequency, which is all about how often those waves are rolling in, the number of waves that pass a point in a given time. And it's measured in Hertz, meaning cycles per second. So a wave with a frequency of 1 Hertz means that one complete wave passes a given point every second.
So a higher frequency basically means more waves are zipping by every second. Okay, so we've got crests, troughs, amplitude, wavelength, and frequency. Is that the complete anatomy lesson?
For transverse waves, yeah, those are the basics. Now let's circle back to those key differences between mechanical and electromagnetic waves that we touched on earlier.
Okay, this is where things get really interesting. Mechanical waves need a medium, but electromagnetic waves don't. But what other consequences come from that fundamental difference?
Well, one consequence is their speed. The speed of a mechanical wave depends on the properties of the medium it's traveling through. So, for example, sound travels faster in water than it does in air.
So, if you're underwater and you yell, your voice will reach somebody further away faster than if you yelled in the air.
Precisely. Now, with electromagnetic waves, they always travel at the speed of light in a vacuum. But their speed can slow down slightly when passing through different materials. Like when light bends as it enters water or glass, it's because the light waves are slowing down a little bit as they enter that denser medium. But here's another crucial difference. The way these two types of waves transfer energy is also fundamentally different.
This is where they show off their different dance moves.
Right.
How do their energy transfers differ?
Exactly. So mechanical waves, they transfer energy through the vibration of particles in that medium. Think about sound waves again. They travel by causing air molecules to bump into each other, like a microscopic domino effect, creating those areas of high and low pressure.
So it's like one molecule bumps into the next, and the energy keeps moving along the chain. What about electromagnetic waves?
Electromagnetic waves transfer energy through oscillating electric and magnetic fields. And these fields, they don't need any particles to propagate. They can exist and travel even in a perfect vacuum.
So it's almost like electromagnetic waves are creating their own medium as they travel.
That's a great way to think about it. Now, let's delve a bit deeper into this incredible world of electromagnetic waves and talk about the electromagnetic spectrum.
Okay, I'm ready to ride that wave of knowledge. What's so special about the electromagnetic spectrum?
Well, it's not just one type of wave. It's a whole family of electromagnetic waves, ranging from low-energy radio waves to high-energy gamma rays, all arranged according to their frequency and wavelength.
It's like radio waves and gamma rays are somehow related.
They're all part of the same electromagnetic family, but what sets them apart is where they fall on this spectrum.
Okay, so walk me through this family portrait then.
Sure. So at one end of the spectrum, we have radio waves, which have the longest wavelengths and the lowest frequencies. And these are the waves that we use for communication, broadcasting, and even radar. As we move along the spectrum, the wavelengths get shorter and the frequencies get higher. Next up, we have microwaves, which we use for cooking and satellite communication.
Ah, yes, microwaves. What comes after that?
Then we have infrared radiation, which we feel is heat. That's why you feel warm standing in the sunlight. Then, right in the middle of the spectrum is a very narrow band of wavelengths that we can actually see visible light. All the colors of the rainbow are just different wavelengths of light. Red has the longest wavelength, and violet has the shortest.
This is incredible. So as we move past visible light, we're entering the higher energy part of the spectrum. What's lurking there?
First, we encounter ultraviolet radiation, which is what causes sunburns. Then we get to X-rays, which can penetrate soft tissue and are used in medical imaging. And finally, at the very end of the spectrum, are gamma rays, which are produced by nuclear reactions and have the shortest wavelengths and the highest frequencies of all.
So we have this whole range of electromagnetic waves, all traveling at the speed of light, but with the drastically different properties and applications. It's an incredible spectrum. You mentioned that the electromagnetic spectrum is arranged according to frequency and wavelength. Is there a connection between those two?
Absolutely. There's a fascinating inverse relationship between frequency and wavelength. As the frequency of an electromagnetic wave increases, its wavelength decreases, and vice versa. So
Radio waves with their low frequencies have those long, lazy wavelengths, and then gamma rays with their incredibly high frequency, they have those super short, energetic wavelengths. It's like a cosmic seesaw. As one goes up, the other goes down.
that's a great analogy. Now, we've covered a lot of ground with transverse waves and the electromagnetic spectrum, but there's a whole other type of wave that we need to explore. Longitudinal waves.
Okay. Let's dive into that in part 2 of this deep dive. Okay, so we've navigated, the peaks and troughs of transverse waves. We've explored the vastness of the electromagnetic spectrum. Now let's shift gears. Talk about longitudinal waves. What makes them unique?
So if you think about transverse waves, they're all about those up and down movements, like a boat on the ocean. Longitudinal waves are more about this like back and forth motion, like a spring being pushed and pulled. So instead of crests and troughs, we have compressions and rarefactions.
Okay, imagine a slinky. It's all stretched out. And then you push on one end, you see those areas where the coils are all bunched up, that's the compression. And then areas where they're spread out, that's the rarefaction.
Exactly. And it's those compressions and rarefactions that are carrying the energy in a longitudinal wave.
And I know that sound waves are like the prime example of this. Like, it's so fascinating to think that when I'm listening to music, those sound waves are creating these like tiny little compressions and rarefactions in the air around me.
It's like an invisible dance party.
Yeah, it really is. And the frequency of those compressions and rarefactions determines like the pitch of the sound that we hear. So a higher frequency means a higher pitch. It's amazing to me that something so small, these like vibrating air molecules, can create such a wide range of sounds, from like the lowest bass notes to the highest bird song.
Yeah. And what's even more remarkable is that longitudinal waves aren't limited to just sound. They show up in other really fascinating areas like medical imaging.
That's right. Ultrasound waves are longitudinal waves that are used to see inside the human body. Like, I remember when I was pregnant, the ultrasound technician used those sound waves to create an image of my baby. It's amazing how we can use sound to see things that are hidden from our normal vision.
Yeah, ultrasound is a perfect example of how understanding the properties of waves can lead to these really incredible applications. And those same principles apply to even larger scale phenomena, like earthquakes.
Oh, you're talking about those seismic waves that travel through the Earth during an earthquake.
Exactly. The fastest type of seismic wave, called a P wave, is a longitudinal wave. and it travels through the Earth's interior, compressing and expanding the rock as it goes. And by studying those P waves, scientists can learn about the internal structure of our planet.
It's mind-blowing to me how these waves, whether it's sound waves or ultrasound waves or seismic waves, they play such crucial roles in our world. It's like this hidden language of energy transfer.
It really is all about understanding how energy moves
Yeah.
and interacts with matter. And now that we've explored these fundamental wave types, transverse waves, longitudinal waves, mechanical and electromagnetic, let's think about how this knowledge connects to our daily lives.
Yeah, besides the obvious examples, like listening to music or feeling the warmth of the sun, what other ways do we encounter waves in our daily routines?
Well, think about the electromagnetic spectrum again. We harness such a wide range of those waves for our everyday needs. I mean, from cooking our food in a microwave to communicating wirelessly via radio waves, they're literally woven into the fabric of our lives.
It's true. I can't imagine life without my Wi-Fi. I'm riding those electromagnetic waves constantly. What about mechanical waves, besides sound? Are there other everyday examples of those?
Oh, yeah, absolutely. Think about those little ripples that dance across the top of your coffee when you stir it, or even the vibration of your phone when it rings. Those are all examples of mechanical waves in action.
You're right. I never even thought of those things as waves before. It's like I'm seeing the world through a wave-tinted lens now.
That's the beauty of understanding these fundamental principles. It opens up this whole new level of appreciation for the interconnectedness of everything around us.
So, why should we care about understanding waves? What's the significance beyond just appreciating, the beauty of nature?
Well, understanding waves isn't just about appreciating nature. It's about harnessing their power for practical applications. By understanding how waves work, we can manipulate them to solve problems
Nice.
and create new technologies.
It's true. I mean, think about medical imaging with ultrasound, or how we use electromagnetic waves for telecommunications, connecting people across the globe instantaneously. That's all thanks to our understanding of wave behavior. What are some other areas where we see this kind of innovation driven by wave science?
Well, in the field of renewable energy, harnessing the power of ocean waves to generate electricity is a really promising avenue. And there's also ongoing research into using sound waves for medical therapies and even for targeted drug delivery.
It's incredible to think about, the sheer range of possibilities when it comes to harnessing the power of waves. It seems like the more we learn, the more potential we unlock. But I'm curious, what's the key takeaway from all of this? What's the most important thing for our listeners to walk away with after this deep dive into the world of waves?
Well, I think the key takeaway here is that waves are more than just those mesmerizing ocean swells or even the sounds that fill our ears. They're fundamental to the very fabric of our universe. They're carriers of energy and information that shape our reality and fuel our technologies.
Yeah, it's mind-boggling to think about, from the smallest ripples in a pond to the vast expanse of the electromagnetic spectrum. Waves are everywhere, constantly interacting and influencing our world in ways that we're only beginning to understand.
And that's what makes the study of waves so captivating. It's a journey of constant discovery. The more we learn about the properties and behaviors of waves, the more we realize the sheer breadth of their influence and the untapped potential that they hold.
It's true. I mean, we've seen how understanding waves has led to, breakthroughs in medicine, communication, even renewable energy. But what about the future? Considering the endless possibilities of waves, how else might we harness their power to solve problems or create new technologies?
Well, imagine a world where we can use sound waves, not just for medical imaging, but for targeted drug delivery. Directing medicine to specific cells with pinpoint accuracy. Think about harnessing the immense energy of ocean waves to power entire cities, providing clean and sustainable energy for generations to come. Or envision a future where we can manipulate light waves to create new forms of communication, transmitting data at speeds that dwarf our current capabilities.
Those are some really exciting possibilities. I mean, it makes you wonder what other groundbreaking discoveries await us in the world of waves, what other hidden languages of energy and information are just waiting to be decoded.
Well, the journey of scientific exploration is never ending, right? Each new discovery kind of unlocks new avenues for innovation and understanding. And waves, with their seemingly simple yet profoundly complex nature, are a true testament to that spirit of exploration. They remind us that the universe is this incredible symphony of energy and motion, And by tuning into those vibrations, we can unlock a world of possibility.
So, to our listeners, we encourage you to continue riding those waves of knowledge, stay curious, and never stop exploring the wonders that surround us.
Because who knows? Maybe you'll be the one to make the next groundbreaking discovery, to ride that wave of insight that transforms our understanding of the universe. Until then, keep exploring.